We've had the idea of a bell-shaped curve come up a few times throughout the course, and now we're going to get into what we call normal distributions, which are a particular kind of distribution, and the shape that the distribution follows is that of this sort of bell shape. So we would say it's definitely symmetric, it's unimodal, and then bell-shaped just describes how rapidly the curve tapers off into the tails. So bell-shaped already implies symmetric and unimodal. A normal curve is completely determined by the mean and the standard deviation. So we use this notation here where the n stands for normal. The first number in parentheses is the mean. We're using notation for a population mean and a population standard deviation here. And unlike some other distributions, once we have decided that it's normal, if we know the mean and the standard deviation, the whole distribution is completely determined. Now, this doesn't have to be a population mean mu. It can be a sample mean x bar. Or a population mean mu. And the standard deviation can come from a sample, in which case we would call it S, or from a population, in which case we call it sigma. But it ends up being a little bit simpler to just assume we're talking about a population so that we can refer to these symbolically. For example, if we consider this randomization distribution for the hypotheses p is equal to 0.5 or p is greater than 0.5, so this is a randomization distribution for p hat, a sample proportion p hat, and from 125 soccer games, so we have n equals 120 soccer games, so we have n equals 120. It looks like this distribution is approximately bell-shaped, and therefore we can approximate it with a normal distribution. What we do to get that normal distribution is we take the mean from our randomization distribution, or we take the mean that it should have been, right? This one is centered very close to 0.5, but it should end up being centered at the null parameter, which we'd call p naught equals 0.5. And we make our normal distribution also be centered at 0.5. Then we take the standard error that we see here for our randomization distribution and just generate a normal distribution that has standard deviation equal to that standard error. So that's 0.045 in this case. And that gives us a curve that we can use the same way that we use a randomization distribution. My randomization distribution had the p hat value here of 0.583, and my normal distribution has the p hat value here also of 0.583. Now, in the randomization distribution, we could always explain the p-value by saying that we count dots, right? We count dots and we figure out the proportion of all of the dots in the graph that are in that tail. What we do with these normal distributions is we use the fact that the area is always equal to 1. That area I'm talking about is the total area under the curve. So if I'm interested in the proportion of that area that's in this tail, well, a proportion of 1 is just itself, right? So that we set it up so that the p-value is just equal to the tail area. Now that's not something that we could calculate easily, but it is something that software can calculate easily. We could give a rough estimate and say, oh, I don't know, it looks like maybe about 5% of the total area under that curve is in that tail, but people aren't very good at getting those estimates really accurate, and software is very good at coming up with this 0.033 for the area under that tail.